Well, looks like we can get going. Welcome back, everyone. So we're closing out the second week, and we've been working really hard. So our reward is we won't have class next Monday. We already have a holiday lined up. What that's going to affect is our quiz. Quizzes are usually due on Mondays, but this is going to be the odd one out. This one's due on Tuesday. I obviously won't collect on a holiday. That just seems kind of rude and inconsiderate. Aside from that, I don't have a great deal of announcements, so I'll turn it over to the class. Any questions or comments to start us out today? Okay, well, maybe before we jump right in, I want to show folks one more thing in WebAssign. I've been pulling it up a lot, but this one's again about requesting an extension on a homework. Reason why I want to show it again is once a section goes past due, we have to go and find it. And I think WebAssign does a good job of sometimes burying things. So let me show you what it looks like when a section goes past due. So temporarily, let's take a moment while I log in here. Oh, that's not right. Let me try again. Okay, we're finally in. So once you get into WebAssign, go to your home for the class. It looks about like this. Your assignments on a list of what's due next is always going to appear here. And if you did request an extension, sometimes it goes onto a weird spot. Say, if section 1.2 was extended to maybe September 8th, it'll go right here out of order in the middle. I'd probably make sure I go to the earlier section in that case. But if you have a section that did go past due for whichever reason, then take a look right under here under past assignments. That's where they're all going to end up. You can click on this, and anything that doesn't have a score where you would like it to be, mine are all zeros, I've been ignoring them. But you can go to any one you'd like to revisit and click on the request extension button. So that's what happens when something goes past due and you need to request an extension in that case. And the process is the same. Click on here, select a time, date, and just a reminder, you don't have to say anything that's personal going on in your life unless you think it's something I should know about related to class. So if something busy happened and you just couldn't get it done, you don't have to put anything there. You can just request a date. Yeah, go ahead. It'd be right at 6 p.m. when class starts, which is kind of unusual, but I'd say if you know you have one that's about to go past due right when class starts, you can just request the extension ahead of time if you know you won't be able to get to it. Other questions about that so far? Okay, well, that was my blurb on requesting extensions. I think we've done this a couple times, maybe a few times, but reminders never hurt. And now we're back to section 2.3. I remembered my digital pen today, so I'm not going to have you suffer watching me go to the chalkboard, try and draw things. But before we go to there, any last questions, folks? Okay, let's dive right back in then. We're nearly done with chapter 2, but we'll come back to 2.4 once we start chapter 4, since those topics go together. And this is where we left off last class. We were looking at different kinds of histograms and the different types of shapes that they can take. And our discussion ended on discussing unimodal histograms versus bimodal histograms. I recreate all the graphics here, so it might look a little bit different than what was on the chalkboard, but these still qualify as good sketches for those kinds of graphs. What makes this one unimodal is this is the main peak here, where most of the data seems to be aggregating. Data is aggregating around it and peaking right here. Because it has just one major peak, we call it unimodal. On the bimodal set, we consider both of these main peaks. This one here and this one there. And if the graph did look slightly different, suppose, for example, maybe we extend it a little bit to the left, put some observations here, more observations here. As that graph stands, we'd still call it bimodal, having two main peaks, because there's just not enough aggregation of data in this location for it to be trimodal, or we would just say multimodal more likely. If that becomes a higher peak, where the data is accumulating more and more, even just on that one spot, then we would say, yes, it's looking multimodal. A lot of these are judgment calls. There's no formula here, it's all qualitative. So kind of go on these notes is to draw a lot of pictures so we can see what do the borderline cases look like. Well, any last questions, folks, on unimodal versus bimodal and so on? Okay, and the next big topic is symmetry. If our data set is symmetric, then that's usually the best case situation for us. So if you say did a graduate major project, you actually had to collect data and analyze, if your 50 observations fell into a symmetric display, then all your statistics are going to be much easier to run through. If you have asymmetrical data, everything starts to get a little bit harder. Your conclusions become less powerful, your confidence intervals will become wider, that we'll discuss later. So first, let's take a look at something that's like almost perfect symmetry, almost idealistic. So if you collected random data and your graph looked like this, we'll put a major peak, this time roughly in the center if the data is symmetric. We'll have observations falling down as we move away from the main peak. And let's see, how many do I have here? I think that's about how I draw it. I'm trying to make all of my rectangles be equal in width. I'm only drawing freehand, so it's really to the best of my ability. But if this was your data, you would say that this is highly symmetric. That deserves an exclamation mark because that's kind of our best case situation, having data that looks like that. It doesn't have to be highly symmetric data. It could be pretty terrible. And if that's the case, we would say the data is skewed. But let's look at a borderline case where we would still say, yes, the data is at least roughly symmetric. Any questions first with that first sketch there? Okay, so my next one, it's still going to qualify as being symmetric. We're forgiving with that to an extent when we go to select our statistical procedures, but it definitely feels like it's borderline. I'm going to draw it where if it was much worse, even a little bit, we would probably start to say skewed and we have to select a different procedure. So here, I'm going to make it somewhat similar. I'll put a main peak, this time not exactly in the center. We'll have more data falling to the right than to the left. If I stop right here, I'm going to put a little bit more, but suppose I did stop right here. This is now extremely asymmetrical. What we mean by symmetry is, on the one that's highly symmetric, if this is on printed paper, you should find a way to put in a vertical line, say this one, so that if you fold the paper over, the heights of all those rectangles should roughly overlap. Not perfectly. If you collect, say, 50 observations, and it was perfectly symmetric, people might wonder if maybe the data is fake at that point, since that's so unusual. But if you can fold it over and it roughly overlaps, we have some really great symmetry. Over here, if we try to put down any vertical line and fold the paper over that vertical line, nothing's overlapping. Say, for example, a line here. Well, the only thing that would overlap is the first rectangle, but then this, if we fold it over, would fold to that location. It had nothing overlapping. And so now as it stands, this is not symmetric at all. Let's improve it, see how we can make it at least roughly symmetric. Any questions first so far? Okay, let me put down now some rectangles going off to the left, but not too many. Maybe about like this. You know, actually, let me take that one off. Sorry, if you're working in pen, I'll leave it like that. That's our data there. If you have that kind of data, it's not nice, it's not wonderful, but the asymmetry we see is not yet hugely problematic. Sure, there's no great place to put a center line on, but still, if you fold over, maybe say around here, there's at least some overlapping. It's not terrible. And this is data that we would call roughly symmetric. So in other words, when it comes to symmetry, we are pretty forgiving. Don't think of symmetry as something that has to be perfection. Even this graph wasn't perfect. It had different heights on these rectangles on purpose. But when it gets bad enough, that's when we are going to start to call our data skewed. Well, any questions or comments so far? Okay, let's pause on these definitions and pictures for just a moment and look at the histogram immediately up. That was just there for an example, so we could look at histograms and discuss it. But now that we have a little bit more language, let's take a look at this thing. Well, if we see this, we would have a main peak right here. And this right here, there's one observation in that location, but that's not enough for us to consider that a secondary main peak. So for these data, we would call them unimodal. Next, didn't want to delete that, sorry about that. Next thing we might discuss is, what about the symmetry on this? Would you agree that it's roughly symmetric or bad in this case? So I'm saying not looking too good. I would agree. If we put, say, a vertical line somewhere, well, it's always tempting to put it on the main peak, but a vertical line here for symmetry, imagine that's perfectly vertical, not really looking so great, right? This one folds over to this location. It's kind of a mismatch. This folds over to empty space. And this one folds over to this location, more empty space. So in this case, I would consider this to be not symmetric. We'll have another word that we're going to give to that later. We're going to call it skewed, but we have to discuss the direction at the same time. Then the next issue about this, which definitely gets tricky, is keep in mind, some of the observations can be highly, highly unusual. Like when we were looking at the crimes on campuses, the University of Central Florida was absolutely an odd one out. There was a great degree of separation from here to here. But if we look at our current display, on this histogram, one individual lied in this location, but this separation is small. That's not enough for it to be necessarily an outlier. So I would say here, even though it looks concerning, it needs to move even further away from the main grouping of data before it becomes highly unusual, like on the last problem. So I would say there are, let me circle this just to tie the idea together, no apparent outliers. So that's what I would say for this situation. Any questions or comments about this at the moment? Okay, so that's our wild world of the histograms. And just a reminder, once again, all the histograms are trying to tell us is how many observations fall into well-defined ranges. So if we looked at the main peak, it's saying 5 individuals had a pH for their joint fluid that was from this number to about maybe 7.3. So it's just saying, where is the data when you're looking at a histogram? Now let's get into issues of skew, but first, any questions at the moment? Okay, so when things become not symmetric, we want to be a little bit more descriptive. It means it's skewed in one direction or the other. Let's go and put those definitions or pictures right down here. A histogram that is not symmetric, we consider it to be skewed. And here they say, we have something that's positively skewed or right skewed. I'll use those words interchangeably. I think I often just say right skewed or left skewed. And this happens if the upper tail of the histogram stretches much farther than the lower tail. That definitely needs a picture, right? The words just don't do it. So let's do something immediately for positively or right skewed. So right skewed data, it's going to look something along these lines. You'll have a lot of data accumulating in one location. It can start falling off slowly or rapidly. Let's make it gradual at first, and then a very, very rapid dropping off of data. So that would be about the picture for data that's right skewed. Now when it says the upper tail of the histogram stretches out much further than the lower tail, we're meeting these values here. That's the right tail. There isn't even a lower tail at all on this to compare. So when we say right skewed, we mean the direction the data is trailing off to. It's trailing off to the right, so right skewed. So right skewed. Right skewed data, again, is problematic to work with. There's various tricks we can use to try to fix it. But at the end of the day, it's not a pretty sight when you have it. We have to work a little bit harder. Any questions with right skew? Okay, let's maybe add some context to this one just for fun. Right skew data is actually pretty common in a strange sense, and here's a way that it could come into play. Oh, I didn't mean to delete. Let me try again. So we can say that this axis represents maybe time. The vertical axis in a histogram would be frequency, number of observations. And this could be some kind of maybe biological experiment. Maybe this is amount of time. Rats survive after injection of a virus. That's pretty morbid, but that's something that scientists will look into quite a lot for some of their experiments. This becomes right skewed because if the virus is deadly, a lot of the maybe rats or guinea pigs are going to die off pretty quickly. But as time goes on, some of them are going to be the survivors. There's only going to be a few that just survive a little bit longer than you would expect. In fact, we could even put something out here, which is now a borderline outlier. Survival times, whether they be mice in a laboratory or even light bulbs in a classroom, have this display. Some of your light bulbs are going to just die out when the manufacturer expects, but some production runs are just better and you win the lottery on your light bulb. It could last a really, really long time. So right skew data, survival times is a very, very common context. Well, any questions, folks, with this display here? Okay, let's do left skewed next. To me, left skewed data, it's kind of strange in a certain sense. It's a little bit rare in that it's something I don't run into a lot, data that's left skewed. And if I had to come up with an example, sometimes it's a bit of a challenge. So while we're drawing this, if you can think of a context where you would get data left skewed, let me know and we'll add it on here. So first, let me just do a quick border. And now for left skewed, here's what they say for us. You're going to have negatively skewed or left skewed data whenever this happens. The lower tail is much longer than the upper tail in that case. So here's another quick histogram for when that can emerge. So like before, we're going to have a main peak somewhere. It may not be as prominent as some of these examples. It could be kind of diminished. But I'm going to let some data move to the right in that kind of shape. And now at this stage, I would consider where the red dot is hovering, that would be the right tail to this data, where the data is just trailing off to the right-hand side. But we want something that's left skewed, so I'm going to make the left tail much, much longer. So I'll start putting in data that goes like this. And let's put in something that would look almost definitely like an outlier. So that's our distribution here. I would say this one's kind of tough at first to determine the skewing because we have to look at the right tail here and compare it now to the left tail. The left tail is definitely going to be longer. Yeah, go ahead.
Just to clarify, the left tail is the lower tail, correct?
Yes, on the lower end of the axis. Exactly. And the upper tail would be on this end, the upper tail, the axis. Other questions so far? Okay, so that's our data. It's left skewed. This time, well, it's only a little bit more left skewed than it is right skewed when we look at the two tails. But if there is a longer trail going off to the left, That would be the direction of the skewing on this one. And if you look at data and it's really hard to discern, is it left or right? It's probably just roughly symmetric, and that's probably the better answer in that case. Well, can anyone think about context for data that might look like this? I had one that I thought about before class, just in case, because again, these are kind of tricky. Here's the one that I always kind of go to. Something that's left skewed might look like this. I'm going to put 0 here and 100 here. And imagine, like, say, a really, really terrible class, maybe like a physics class. This could be exam scores on a difficult physics exam. Physics is definitely not my wheelhouse, so to me, that would be something that's scary. And the reason you see left skew on scores is, well, if that's about 70%, then people typically, if the exam is well written, are going to accumulate in around that range. If there's extra preparation, everyone's doing a good job, we'd hope the main peak is around, say, 90%, right? But there's a definite upper cutoff. This would be an exam where no one got 100%. And as you go off to the left, some people did a little bit worse, and maybe this person didn't show up or something like that. But that would be a picture for whenever you're dealing with left skew. There's certainly other examples. That's not the only kind of data that's left skew. It's just kind of hard to come up with those examples. I'd have to Google search it to get a good long list. Well, any questions, folks, on getting through the pictures for skewing? Okay, now, just as a heads up on all this kind of thing, we want to calculate things like, let me scroll for just a moment, the center. We want to put a number there. We don't want to just eyeball it and say around here. We want to calculate a number for the spread as well. Instead of just saying from 0 to 29 is our range. And sorry, I just noticed a typo when I try to recreate this. That should be way out over here, shouldn't it? 29 is in that location. I think I did it right on the chalkboard, but when I redrew it, I misplaced that. So we would like to calculate center and spread, but the way we calculate center and spread is going to depend on the shape of the data. If you have symmetric, or even just roughly symmetric, like right here, we'll be using the sample mean, just the ordinary average, and we'll be using the sample standard deviation for these kinds of situations here. They do a very good job of saying where's the center and how spread out the data is. But when the data gets really bad, we're going to see exactly why in chapter 3. For bad data like skewing, the sample mean actually doesn't do a good job of saying where your center is. The skew has leverage. If it's right skewed, your sample mean gets pulled to the right, becoming less and less accurate. And the worse the skewing, the more it's getting pulled in that direction. Likewise, for left skewed, if you go to calculate a sample mean, it won't represent the center anymore. It's going to be pulled in the direction to the left. So the big takeaway to all this is the shape of the data tells you what statistics you'll use. You'll either use a sample mean or a sample median, the 50th percentile, depending on symmetry versus skewing. So that's why we're taking a look at so many histograms, and we'll take a look at just one last one, kind of to tie off these ideas. Any comments or questions so far? Okay, well, here's the last example of this section. And we looked at these data before just to get a feel for what's a histogram. That's always a good question. So just a reminder, what we have here on the horizontal axis, let me zoom in on this a little bit more, is ratio. It's the ratio of how much the CEO makes against the median worker. So if you pick just a random value like 1,000, that means the CEO gets paid 1,000 times as much as the median, the typical worker. So these data, when it comes to pay, really almost anything when it comes to money has a definite shape that looks like this. So let's now take a look at the instructions. We want to describe shape, the center, and the spread of this distribution. Starting with shape. Well, again, like we said, if the data is numeric, you'll know what the shape ought to be for this data. And there's several things that we can answer here. Let me put down just some guidance on what we're looking for. The question is about shape. We want to know modes. Is it unimodal? Is it bimodal? And so on. We want to know about symmetry or skew. That's spelled differently. Let me try again. W for skew. We want to know, is the data symmetric, at least roughly symmetric, or is there a prominent skewing to the data? And we also want to know if there are outliers. So when it comes to shape, those are going to be the big things that we're really looking for. With that in mind, let's take a look at this. I guess we can go down the line. How about for modality? Is it unimodal, bimodal, or worse? Absolutely. The main peak is this right here. Then the data is just falling off very, very rapidly. I mean, that's a good thing. If it didn't, that means CEOs are getting paid just a very, very large astronomical amount of money. Some of them are, but not a ton of them. As you go down here, it just keeps dropping. And let me zoom in again. If you can't see it too well, especially in the back of the room, this problem doesn't even print well for exams. I did that once and that was a mistake because there are actual histogram heights right here. It's just really, really small. This is a very big data set. So you have observations here, but they're not main peaks whatsoever unless the histogram looks something like, say, this. You have to have data accumulating there in earnest for it to be bimodal somewhere. So even if, say, this ticked up a little bit, it's still not enough for it to be bimodal. It would have to be even more substantial, much higher. So we'll state first for shape. Let me remember to zoom back in. This is unimodal. Then how about symmetry versus skew? Any volunteers for the situation on these data? Some saying right? Go ahead. Yeah, this will be rate skew data, absolutely. So again, when you're thinking about skew, just think in your mind, where is it trailing off? And this is where it's trailing off, very, very far to the right on this one. These are pretty tremendously skewed data. So it's unimodal, right skewed. And now outliers have to be something we're a little bit careful about. Let me remind you of things to avoid. When you see data like this, where an observation is separated, but not by much on the histogram, I would say it could be borderline, but it's likely just not an outlier in this case. These are the ones we're very, very interested in. That's an observation orders of magnitude away from the main grouping. And so now on this display, our current scenario, would you say there are outliers or not outliers? I agree, there's definitely outliers on this. We have observations here that are very far away from what I consider the main grouping of data, going from here around to here. So that's pretty far away. Some people might decide those are outliers as well. I think that's where it's getting kind of borderline. Now, this is a tough process, right? Because that was purely visual, nothing else. But when we're in chapter 3, we'll get a rule of thumb to determine when things are outliers or not. Just keep in mind it's a rule of thumb, so it's not exactly a formula either. It's just extra guidance. So I'd say here on this particular problem, there are outliers on the upper end around 2,000. I don't know what the observations are, how many, or what they are exactly. I just know there's observations around this area, which means there are some companies that have chief executive officers who get paid 2,000 times as much as what would be typical. And there's certainly going to be companies that are probably even further to the right there. This is a limited data set. Well, we took care of shape. That was a lot of information we put in. Now we'll do center and spread. These go a little bit faster. Any questions at the moment? Okay, So center is always pretty tricky because we haven't done any formulas yet. That's going to be in chapter 3, the very next section. But what we're trying to do with center is decide where is all the data accumulating. We did this once. Here's the reminder real quick. When we looked at these data, we said it was centered around 5. Maybe 4 would have been a good answer. I'd say 6 is not bad either. But we said around 5 because, again, that's where a lot of the data is aggregating, concentrated in. So now imagine you don't have dots. You're just looking at a histogram. We still want to know what is the most typical value. Any volunteers for the value that represents the center the best? Would it be, say, 500, or should I go left or right? Yeah, let's go left. I had to kind of imagine if I go left to around here, would you say that's about the center, or should I go a little bit to the right or to the left? A little bit to the left still, or to the right? Yeah, I'd say about there. I would say right around here. I'm not trying to hit it perfectly, but that's pretty close to the center. Now, here's one way to do it if you wanted to make it more of a process. Imagine on this histogram, these have areas. Well, I mean, they do, right? Each one of these rectangles have an area, and I wanted to divide the area in half. In order to do that, well, most of my area is in this rectangle, right? There's less than half of the area going off to the right. So I don't necessarily want to cut this in half to get the center. Maybe we could cut it to right about here. So right at this location, imagine that's a perfectly straight line. What I'm saying is I should have about the half of the area to the left of this purple line. I think of what color that was. And I should about have half of the area to the right of it, now shaded in black. So we can't do it perfectly. We're not meant to. We're just trying to eyeball it. But I'd say right around where the red dot is, right here, the area that's in purple is equal to about the same as the area that I'm shading in black. I was shading it kind of poorly. These also qualify. These ones aren't contributing much, but they're also part of it, even these far outliers. So right where the red dot is, that's where I would consider the center to be. Let's see if we can estimate it next. So it goes 0 to 500. So right here is about 250. So maybe right around here, I don't know, what would you say, about 200, 175? Something like that. If you were answering this as a quiz problem, as long as your answer is in that neighborhood, I'm not too worried about it being like the best estimate. Let's say right here, that's our value. I'll take these off just so it's not a distraction. And now we can say that the center, I guess that should be in blue. The center is a ratio of, I'll put this approximation symbol to say I'm rounding, but it's totally optional if you don't use that. And I think we said maybe 190 altogether. Well, any questions, folks, on estimating that center here? Okay, so what we're saying when we say center is that's just the most typical value in this data set. Most companies that was surveyed had the CEO getting paid about 190 times as much as the typical worker. Now, here's the wild part of this. This was skewed data, right? That means the sample mean, which we call X bar, is not going to be a good description of the center. In fact, where people were kind of looking, where everyone was directing me, this is the 50th percentile. That's the median. So although this is extra, let's say it right here. Once I find a spot to write it in, M, we'll use uppercase M to stand for the 50th percentile. 50th percentile means half of the observations are going to be lower than about 190, and half the observations are going to be larger than about 190. And the name we give this is median. So the median, because these data are skewed, describes the center very well. In fact, in the experiment we just ran where the class kind of picks where the red dot goes, people are remarkably close when they go to estimate this. It's like the human mind is just kind of programmed to find out where a 50th percentile would be. Now, here's the sad fact. Let's add one more extra thing. Because this is right skewed, we have that the sample mean, just the average of all those observations, we use X bar to represent the average, is going to be larger than the median M. The way that works is you could build this histogram, say, out of, for your horizontal axis, just get a big 2x4. For the height of the rectangles, start stacking bricks. And where X bar goes is where the whole thing would bounce like a teeter-totter. It's the location of a fulcrum. So these outliers have extremely high leverage. And the only place this would balance as a real physical object, again, imagine the axis as a 2x4, these as just stacked bricks, all of the same density and mass. The sample mean, if I had to guess, is probably going to end up right here. That's where the whole system balances. And this is the location of X bar. So X bar is pulled to the right, becoming inaccurate in describing the center any longer. If the skew is worse, it just becomes more inaccurate, keeps on going in that direction. So knowing the shape of the data really already comes down to this. We are going to calculate the center. We have to pick the 50th percentile because the sample mean is just going to do a horrible job saying what's typical. So that's how the center goes. And for spread, well, spread is a little bit tricky with where we're at right now. We did it once on our first data set, but we just mentioned where the minimum goes and where the maximum goes. We'll do that one more time, and then chapter 3, we're going to improve on describing how spread out data is. So last one, I'll just say here, spread. Once I spell spread right, one more try. And I'll just simply say the data ranges from, I'll use this symbol again, approximately, well, that's tough. I'm not sure if anything's around 0, right? 0 would mean the CEO is getting paid nothing. That could happen. And possibly the CEOs just try to do their taxes right. Maybe it's a year where they signed on, they're trying to make the company profitable, and they're only going to take the wages once their stock market gets so high. I mean, 0 is possible for a CEO. They probably have funds elsewhere. So I'll say from approximately 0 to approximately same trouble. I don't know how high it goes on this end, but we'll just use what we have on our histogram and say 2000. So the main takeaway of this is analyzing the histogram, its shape, the modes, the symmetry versus skew. Here we're very right skew, and knowing if we have outliers or not. And starting in chapter 3, the big thing we're going to focus on is what is the right statistic for the center? Is it the sample mean or the median? And what is the right thing for the spread? We'll use standard deviations and something else called interquartile range, the central 50%. Well, that's where these notes end so far right here, folks. Any last questions about them at the moment? Yeah, go ahead.
Is the opposite true for the left skew, where instead of the air of little angle thing,
That fulcrum, yeah,
yeah, points to the end instead in the left skew?
it would, yes. So if we look at our left skewed data here, I would say the median, not in the center of the peak because it's skewed left, it'd probably be right around, say, here. But the sample mean, because of the left skewed, goes way over here, a little bit further, that fulcrum. So the sample mean X bar, at the end of the day, it always follows the direction of skewing. So if we're skewed right, X bar is greater than median, skewed left, it'll be less than instead. Other questions about that? Okay, so now we're about ready for chapter 3. In chapter 3, we're going to start actually calculating some of these things, so that'll be exciting. We mentioned words like averages, the X bar there. We quickly start calling it a mean. I felt like maybe the first thing we ought to do before we get too far in that chapter let's calculate some of these statistics. So if you have your calculator with you today, this would be a good time to pull it out just to practice how this is going to go. I'll be using the TID4, and let's go to those 3.1 notes. We're definitely not going to finish them. We're just taking an early look pretty much. So I'll try not to run us right to the very last minute again today. So we're now in chapter 3. And in chapter 3, the first thing we want to do is complete a table that's going to tell us the right statistic to use if we're measuring a center or variability, and dependent on the type of data we have, symmetric versus skew. But before all that, again, let's put in just an optional problem or an additional problem. I'll call this just an example. Let's say we have collected random data and obtained. So no context on this. We're just doing a really fast example on calculating some of these statistics. And our data will be, let's go to 5, 11, negative 13. (24, 30). So there's our data. Here, let's say, calculate summary statistics. So I'll put the results right down below. Now, if you're going to calculate the average of these data, it's really not too bad. You just add them all up, count the sample size, which is 6 observations, and then just divide by 6. But that strategy is going to start to become very, very bad the further we go in this book, because data sets get bigger and other things to calculate, like the standard deviation, is horrendous, even with this really small sample size. So we'll see how all those formulas go, but we're going to crank out the numbers right through the calculator. That's going to allow us to actually focus on the statistics and not get bogged down on loads and loads of arithmetic in the middle. So if you're going to calculate summary statistics on these 6 numbers here, here's the first thing I would do in the calculator. Definitely first turn it on. And now we're going to do this a lot. So if you don't memorize it the first time, I'd say don't sweat it too much. I'm going to have guides that I post on the notes so we can make sure we all have the right keystrokes. But the very first thing you want to click on is the stat key. It's right here where my red dot is on the TID4. If you're using a different calculator like the TID3, it's going to be pretty similar. If you're using something that's not a Texas Instrument, say Casio, for example, it's going to be somewhere on there. If you're not sure if your model will work, definitely let me know what you have and I can take a look into it and do the research. If you're not sure how it goes, if you tried and everything, just send me an email. It could go, hey, Mike, I'm using Casio model number FX something, something. I'm trying to calculate the sample mean. What were those keystrokes? And I'll send you some information. It might be a website, it might be a YouTube video, but I'll be very happy to support how that works on other models. Well, let's give this a try. Click on that stat button, and it pulls up this page here. You'll see edit, calculate, tests. Right now, the option 1 is edit. And in fact, that's the very right thing you want. Hit just enter right here. And what we're doing is we're editing a data set in the calculator. It should look like this, L1, L2, L3. If you bought your calculator used, there might be data inside there. You could just clear it out. You might see your L buttons are gone. They can be brought back. So if it looks really weird, we might have to figure out how to bring it back to its factory settings if you bought it used. But I believe most people should be seeing this. Is that what folks are getting at the moment? Awesome. If that's what you see, take a look at the data to the right here and just start punching it in. If you want observation 2 in, hit 2, enter. Observation 5, 5, enter. And just down the line in that fashion. So this will be 11, enter. And immediately, that negative 13 is the cause of a lot of dead TID4s. It's tricky to put in, and that's a surprising statement. So I'm going to put it in wrong first, and let me know what's wrong about it and how we can correct it. Negative 13, I'll go negative 13. But that's wrong. Anyone see what's wrong with that? Exactly. That's really terrible in the TI-84 calculator. In fact, I remember being a student taking statistics, trying to do this, and you get a syntax error. I spent like a half hour trying to figure out what in the world is going on. It's extremely frustrating. So if you get a syntax error, I would just go to option 2, go to, and it's right there. The calculator is telling you where the error is, that we need to correct that. So like you said, the negative sign is special. That's a mathematical operator. It needs 2 numbers, and there's nothing in front of the negative sign. If I want to just put in a negative 13, that's the negative sign. That's horrific because that little detail could waste hours, half hours of your life. Put in like that, and now it's right. Notice it's slightly raised up, it's slightly shorter. That's how you can tell at a glance that you have the right sign. It's literally a matter of a few pixels on your screen that makes it incorrect or correct. Now, if you hit enter, it accepts the value, it's happy with that. Last one's 24 and 30. And we're done. Notice we don't want to put anything here. We're done with our data set. It says L1, meaning list 1 of numbers, but then it says L17, meaning I'm about to put a 7th number in. That's how I know I didn't skip anything, because if there's 6 numbers, I should scroll up to here and just stop. L16 is what it should say, 6 observations. So if you have all your data in and have it in exactly, now we're ready for the next step. Any questions first? Okay, the next step is, oh, sorry, go ahead. Oh, so if you're right here, you could leave it right here. That would be okay. But what it's saying on this location is L17. So really, it's my way of deciding, did I skip any of the data? Did I double up anything? If there's 6 observations here, then we should stop when we see the 7. And then I went up, but that wasn't necessary. You could have just left it right here. Other questions at the moment? Okay, now to get your summary statistics, here's the button. And this literally saves about 20 minutes of by hand arithmetic. So it's absolutely well worth it. Press the stat key again. Now we don't want to be on the edit. That's if you're changing your data set. We want to calculate something. So use the arrow pad and highlight calculate. The calculator is going to default to the option that it thinks is most likely to be used. And it's right. We're doing 1 variable stats. So we just hit enter right as it looks like this. And once you hit enter, now we're going to get a bunch of statistics. So let's hit that button. Sorry, I forget there's an extra page here. You should see L1 in this location. If it's gone, you've got to use calculator. It could be different. If it's blank, then we have a problem, but here's how you put L1 back. L1 is right here in blue above the number 1. So you hit second key, the number 1, and it brings list 1 back where we put in all that data. Next, frequency list, I will never ever use this. So make sure it's always blank and just hit enter to skip right past it. And with calculate flashing, just hit enter again, and it'll give you all the output that you're expecting. So here's enter one more time. And here's our statistics. That's the average of our data set, about 9.8. That's the standard deviation. And notice that there's a down arrow. Keep on going down. There's the median. That's the 50th percentile at 8. It's close to the mean, so this data is at least somewhat symmetric. And, well, it gives us a min and a maximum. But let's maybe take this screen right here. And these are our summary statistics. So this is the sample mean. And this one, we'll be calculating these soon, is the sample standard deviation. Now, word of warning, we will almost never use that one, sigma x. It's going to always be different. Sometimes it's pretty close, especially if your sample size is large. But sigma x is a population characteristic. This is not assumed to be a census, so we'll almost never use that there unless we knew we had a census. But really, this was more of a preview of just using the calculator. Oh, dang it, sorry about that. I wasn't trying to go right to the minute. And any last questions, folks, before we call it a night? Okay, we'll practice this a heck of a lot more in chapter 3. So if you didn't have it completely memorized the first time, no worries. I'll be showing these keystrokes quite a lot. Well, have a great weekend, folks, and I'll see you Tuesday after the holiday.